The purpose of this video is to remind you again what static equilibrium is, okay? Static equilibrium is a state that an object can be in which there is no change in translational or rotational motion, okay? So it means there's no acceleration translationally in a straight line, up and down, right? And there's no change in motion rotationally, right? There's no acceleration, there's no sudden, like if an object's at rest, it doesn't suddenly start rotating in any certain direction, right? And so the next slide is a horrific collection of things that can happen when things lose static equilibrium. I'm putting this video into the module, and I think it's entertaining, maybe a little scary, maybe a little sad, but I encourage you to watch it because it involves what happens when structures that we depend on for our survival lose their static equilibrium. And that hopefully drives home how important this chapter is, and frankly, how important physics is. And so once you have a sense of what happens when there's not static equilibrium, it helps to remind ourselves of what are the conditions for static equilibrium. What does it mean that an object is in static equilibrium? Well, it means that the sum of the forces in x must equal 0, right? There's no acceleration in x. The sum of the forces in y equals 0. And the sum of the torques on an object equals 0. Okay? And so you can use these to analyze any problem to find out whether or not it has static equilibrium or what forces would be required to give an object static equilibrium. Okay? One caveat. Technically, summation of forces in the z direction also applies here, right? Obviously, if something's truly in static equilibrium, the sum of forces in z must also be 0. But it gets a little bit more complicated. So these are the three conditions we're going to focus on in this class. So remember when I said, the first step to doing any kind of force problem is to say summation of fx equals ma, summation of fy equals ma, right? So when you're doing any kind of a static equilibrium problem, the first thing you should do is write these three things because that's a place to start. These are three equations that you'll always be able to create and then hopefully solve. And I'm not going to leave you in the dark. We're going to do several examples where you're going to see how we use these to analyze the equilibrium of an object. Okay? Before we get there, I just want to do one misconception question. We're talking about like a seesaw here, okay? And this whole thing is length L, right? And that at L over 4, right here, there is a little balancing point, okay? And there's a person over here, and her mass is 60 kilograms, okay? And the question is, assuming this is balanced, in other words, static equilibrium, what must be the mass of the board, okay? So, first things first, we need to make sure we know what are all the forces acting on this object, right? If this is in static equilibrium, we know that sum of fx must equal 0, sum of fy must equal 0, and the sum of the torques must equal 0. Okay, so these are all forces, okay? And in order to analyze the problem, we need to make sure that we have all the forces that are acting on this object, okay? So let's analyze it. We have this person, so this is the weight of the woman. I'll put WW for weight of the woman, okay? And then we also, of course, have the weight of the actual, seesaw. Right? And so remember, if it's a symmetric object, the weight acts at the center of mass. So let's go to the center of mass. That's exactly halfway through. That's going to be L over 2, right? And we're going to have the weight of the board. So I'll do weight of the board, okay? Board, seesaw, same thing, okay? So this guy is acting at L over 2, and or we could also say that it's acting at L over 4 away from the rotational point. And this weight here is also acting L over 4 away from the rotational point, or the axis of rotation. Okay? Because obviously if this is pinned here, that is going to be where the seesaw is going to rotate about. All right. So what are all of our conditions? Well, first of all, there's no forces in the x direction, right? Everything's in the y. By the way, I forgot one force. If this guy is resting on this point right here, there will be a normal force pushing up from him. Okay? All right. So there's no forces in x, so we basically don't have to worry about this. Okay? But y, there's a whole lot, right? In order for this to equal 0, that means that, well, n is in the positive direction, right? Minus the weight of the board, minus the weight of the woman, must all equal 0. In other words, the normal force must equal the weight of the board plus the weight of the woman. Okay? Nothing too interesting in that, right? I mean, we could expect that. We may need to use this. We don't know. But right now the question is, what must be the mass of the board such that this is balanced perfectly at these locations? Okay? So that leaves us then with just that the sum of the torques must equal 0. Okay, well, so let's do that analysis. Sum of the torques are, well, what are the two forces? First of all, we have the weight of the woman, right? The weight of the woman, is that going to be a positive or negative torque, right? If this is pinned here, does this woman make the board want to rotate clockwise or counterclockwise? Well, the answer is probably clockwise, right? Pin there, I put a force there, it's going to rotate like that, right? So that's going to be a negative torque. So that's negative R, right? Remember, torque equals R F sine theta, right? So that'll be negative R. R is L over 2, or sorry, L over 4, times the weight of the woman. That's the force. And the angle that it makes with the board is just 90 degrees. That's 1, so that's what we got for that. Okay? And to make sure I have room, I'm just going to erase this. Weight of the board there. Okay? All right. So summation of torques is that plus, right? I'm going to say plus because the only other force is the weight of the board, and that's pointing down over here. That's going to want to make the board rotate counterclockwise. That has to be a positive torque. Okay? What is my R? R will, if this whole length is L over 2 and that's L over 2, then that must be L over 4. Okay? Make sure you prove that to yourself. That's L over 4, right? Times the weight of the board. And that all has to equal 0, right? This is our torque condition for stability, for static equilibrium, okay? And what does this basically mean? It means that, well, if I add this to the other side, I just get L over 4 times the weight of the woman equals L over 4 times the weight of the board. That cancels, that cancels. This just means the weight of the woman must equal the weight of the board, right? So if these guys are going to be balanced, the board must have the same weight and the same mass as the woman. That's 60 kilograms. That's option D. We, my friends, have an answer. Okay? So this is kind of like just 101 of analyzing the stability of objects. It's kind of like the most basic version. In the next slide, or the next video, we'll talk more and do a few more examples of how to do this for other situations.